I welcome you all in fourth lecture of biomolecules. Before going to the lecture content, I will like to give a recap of last classes, and we have discussed already in the last class regarding the structural formulas of monosaccharide. We have also discussed about the pyran structure, we have discussed about the furan structure and mutarotation and glycoside formation. So, let us continue with the glycoside formation. In glycoside formation, we discussed about the treatment of alpha D glucose with methanol in presence of HCl. So, as we know, alpha D glucose has a polyhydroxy group in its framework. In presence of methanol and hydrochloric acid, it forms two glucosides, methyl alpha D glucopyranoside and methyl beta D glucopyranoside. So, CH3HCl, and what happens basically, one molecule of water come out of from the molecule. To make it more clear, I will use the color code while making the structure, so that you can understand the changes happening in the sugar moiety. So, this is the main scaffold and changes happening here at the anomeric position, and it forms methyl alpha D glucopyranoside. Methyl alpha D glucopyranoside. Its melting point is 165 degree centigrade, and specific rotation, which is denoted by alpha D 25, is plus 158. The other product is methyl beta D glucopyranoside, which is very much similar to the alpha D glucopyranoside. However, methoxy group here attached with the anomeric carbon at the equatorial position. So, again I will use color code to make it more clear. Here it becomes, this is methyl beta D glucopyranoside. Melting point is 107 degree centigrade and specific rotation is negative 33. Now, you can see here these both molecule has formed from the same starting material, only difference is position of OCH3, that methoxy group. In one case it is equatorial in the alpha D glucopyranoside, and in the other case it is equatorial. In one case axial in the alpha D glucopyranoside, and in beta D glucopyranoside it is equatorial. Carbohydrate, generally these are called acetals, and carbohydrate acetals are generally called acetals are called glycosides. And that is why here I have named methyl alpha D glucopyranoside. Pyran is the 6-membered ring in both the cases, and alpha is the position of, reflects the position of methoxy group. So, methyl alpha D glucopyranoside, methyl beta D glucopyranoside. So, carbohydrate esters are called glycosides, and an acetal of glucose is called a glucoside. Glycoside is the general terminology, and for the glucose it is glucoside. Similarly, acetals of mannose are mannonoside. Acetal of fructose are fructoside. So, it is very much clear that carbohydrate in presence of HCl, gaseous hydrochloric acid, and alcohol forms glycoside, and particularly in case of glucose we call them glucoside. Similarly, for mannose, mannoside, and for fructose, fructoside. What is the mechanism of this reaction? So, let us talk about the mechanism for this reaction, mechanism for the formation of glycoside, mechanism for the reaction. What happens in presence of acid? So, here first I will draw glucose, and in presence of acid so here I am adding, this reaction is reversible. Here you can see this reaction is reversible. So, in presence of acid what happens, that it takes proton from the acid and it forms protonated species. So, I will keep the whole structure same, but the hydroxyl of anomeric position will get protonated and that will get converted to OH2. Now, it will have positive charge. Once it attains positive charge, what happens, that lone pair of oxygen of the pyran ring will assist in elimination of this water molecule, and again the second step is also reversible. If it is minus H2O, it will give oxonium species. You can see here, now we get the oxonium species. Now, this oxonium species, which is sp2 hybridized, have two phases for the attack, and these two phases after the attack will give the corresponding two glycosides. If attack is taking place from the beta phase, then it will give beta D glucopyranoside, and if attack is taking place from the alpha phase, then it will give you methyl alpha D glucopyranoside. So, let us attack water molecule. Again I will use the color code to make it very clear. So, if attack is taking place from the top phase, and if attack is taking place from the bottom phase. So, if attack is taking place from the top phase, then it will give you corresponding beta D glucopyranoside. Again this one is reaction, this reaction is reversible. So, let me draw the structure of the molecule. And it will go to the equatorial position. Now, this sp2 hybridize, carbon becomes sp3 hybridize after the attack, and here again acid counter base abstract this proton and leads to the removal of Ha with the corresponding methyl beta D glucopyranoside. So, one thing is very clear that the structure of product, the final product is completely dependent on that at what phase on this oxonium species, that oxonium intermediate alcohol is attacking. So, this becomes methyl beta D glucopyranoside. If it attacks from the bottom phase, so that I will write on the another page, or I will continue here itself. If attack is taking place so here you can see that I have put axial, positive charge is there, and again the counter base of the acid will abstract the proton from the corresponding compound, minus Ha will lead to the methyl alpha D glucopyranoside. Methyl alpha D glucopyranoside. Now, again I will re-explain the mechanism of the reaction. What happened in the presence of acid, first protonation of the anomeric alcohol is taking place, and then with the help of the ring oxygen, removal of water molecule is taking place, that lead to the formation of oxonium intermediate. Now this oxonium intermediate have carbon which is sp2 hybridized, where attack can take place from the bottom face or from the top face. If attack is taking place from the top face, then that leads to the formation of methyl D glucopyranoside, and if attack is taking place from the bottom face, then it leads to the formation of methyl alpha D glucopyranoside. So one thing I will like to mention, that this attack by alcohol oxygen occurs on either face of resonance stabilized carbocation. Now glycosides are, you can see here, these all reactions are in equilibrium, they are all reversible. Here that attack of acid which leads to the removal of water molecule from the acetal, and then further attack by the alcohol, these all steps are reversible, and that is why glycosides are stable in basic solution. Important point, glycosides are stable in basic solution. Because they are acetal, and if we have acidic solution, glycoside can undergo hydrolysis to produce the corresponding sugar and alcohol as a side product. In acidic solution, it gets hydrolyzed, to produce alcohol and sugar. The alcohol obtained here after the hydrolysis is known as A-glycan. The alcohol obtained by hydrolysis of a glycoside is known as A-glycan. This point you need to remember, that when glycoside get hydrolyzed, it generates alcohol, and which is known as A-glycan. To make it more clear, I will like to give you one specific example, and there I am taking a very simple glycoside where the alkyl group is presented with the R. So here I am not expressing the OR substituents, stereochemistry. Now this gets hydrolyzed in the presence of acid, and it will generate the sugar. So, and alcohol. So, this is sugar and this is a glycan, a glycan. Now, what is the mechanism for this a glycan formation? If we go to the reverse pathway, what just now I discussed about the glycoside formation, if we do the reverse chemistry, then we can lead to the glucose molecule. If we start with the glucoside and as well as alcohol. So, let us discuss the mechanism of this hydrolysis. So, again I am taking methyl beta D glucopyranoside. Methyl beta D glucopyranoside in presence of acid. Here I have taken hydronium ion, that is protonated water molecule as acid. So, it will take the proton and it will form the protonated methoxy substitution. Now, it gets protonated. Once it is protonated, again the ring oxygen will help in elimination of this protonated methoxy group in the form of methanol. So, again minus CH3OH, that will generate the oxonium species as an intermediate. Now, again two possibilities exist over here at this sp2 hybridized carbon. One, that attack can take place from the top face and other attack can take place from the bottom face of on this sp2 hybridized carbon atom. So, again let me write water molecule which is available there in the reaction mixture from the top face, this is A, and the other possibility if it attacks from the bottom face. So, here also attack by water occurs on either face of the resonance stabilized carbocation, and this will lead to the corresponding hemiacetal. Corresponding acetal, again this water molecule will be protonated and this will lose the H plus with the help of water molecule. Water molecule will take the proton and it will generate beta D glucopyranose. beta D glucopyranose. Beta D glucopyranose. And same way, if here if we add hydronium species, then again it can get transferred to the corresponding protonated moiety, which can go back to again corresponding resonance stabilized carbocation. Here also I will like to add methanol just to show that these all reactions are reversible. Now, the second possibility, if attack takes place from the bottom phase, that will lead to the alpha D glucopyranose. In a similar way, first it will give the corresponding protonated species, and that will further get processed for the removal of H plus to give the alpha D glucopyranose. This alpha and beta, this represents the orientation of hydroxyl group at the anomeric position. This has to be remember every time when I pronounce this symbol. So, this is alpha D glucopyranose. So, let me go through again. So, we started with the methyl D glucopyranoside. In presence of hydronium species, it gets protonated. That step is also reversible. And then with the lone pair push from the ring oxygen, it liberates the methanol and generates the resonance stabilized carbocation, which can be attacked from the top phase or from the bottom phase. If attack takes place for the water molecule from the top phase, that generates the beta D glucopyranose, and if attack takes place from the bottom phase, then it generates alpha D glucopyranose, the hydrolyzed sugar moiety. As I discussed the concept of A-glycan and alcohol by the hydrolysis of glycoside. So, let me explain it again. Here I am taking example of salicine. Salicine, a molecule, it is a glycoside which has sugar as well as alcohol. So, let me write the structure of salicine. So, this is the sugar part, and now I will use color code to represent alcohol part. This is carbohydrate moiety, and this is A-glycan moiety. This is A-glycan moiety. Now, I hope you understand that when we will do hydrolysis, it will generate this aryl alcohol and corresponding sugar, this carbohydrate moiety, and this in total is known as glycoside. This is a glycoside which by hydrolysis can generate sugar as well as alcohol. Now, I will like to discuss about the anomeric effect. What is the anomeric effect? So, anomeric effect we saw that beta D glucose is more stable, beta D glucose is more stable than alpha D glucose, Let me explain it again. Why beta D glucose is more stable? Let me take the structure here. These two structure. First I will take, so here you can see that in the case of beta D glucopyranose, hydroxyl group is staying quite open. It does not have interaction with the other substituent. So, it will have less strain in this scaffold, whereas in the case of alpha D glucopyranose, there are substituent, this hydroxyl group is there, this H is there, this has certain steric reservation, alpha D glucopyranose, and that is the reason beta D glucose in the cyclic form is more stable than the alpha D glucose. So, here in the beta D glucose, hydroxyl is oriented in the equatorial position, whereas in the alpha D glucose, hydroxyl is oriented at the axial position. However, the preference for the OH group for the equatorial position is not as large as expected, Why is it so? If we see in the alpha D glucose, hydroxyl is axial and it has steric component in it, whereas in the case of beta D glucose, it has very minimal steric, and it should be it is stable. So, population of beta D glucose should be very high, but in the reality relative amounts of beta D glucose and alpha D glucose is 2:1. Relative amounts of beta D glucose and alpha D glucose are 2:1. Why so much still preference for the alpha D glucose? We can understand it by comparing with the cyclohexanol. Let us take example of cyclohexanol. Cyclohexanol, here if we take beta as well as alpha cyclohexanol. In this case, relative amounts for the equatorial and axial is 5.4:1. Here we have huge difference. You can see that in the equatorial it is 5.4 and here is 1. That cyclohexanol mixture has, this is the ratio. Whereas in the case of glucose, it is 2:1. So, in the case of glucose, still we have preference for the alpha D glucose, whereas in the case of cyclohexanol, we have huge preference for the equatorial hydroxyl group. Therefore, there must be a factor which is governing for the alpha glucose formation. What is that factor? Let us discuss about that. When glucose reacts with an alcohol to form glucoside, alcohol to form glucoside, major product is the alpha glucoside. Major product is the alpha glucoside. Alpha glucoside. Because acetyl formation is reversible, as I showed in the mechanism, that was the reason I was explaining the mechanism. So, first alpha glucoside forms as a major product, and then again because of the reversibility it gets equilibrated with the beta glucoside. The alpha glucoside, now it supports the hypothesis that alpha glucoside must be more stable than the beta glucoside. Than the beta glucoside. The preference of certain substituents bonded to the anomeric carbon for the axial position is called. Now, to explain this phenomena, I am introducing this concept. So, the preference of certain substituents the preference for certain substituents bonded to the anomeric carbon for the axial position is called the anomeric effect. Now, let me explain it. Anomeric effect. I have introduced the terminology of anomeric effect. What is this anomeric effect? Because that only can suggest that why so much preference is there for the alpha D glucose. As I have already mentioned that formation of alpha glucoside is more during the reaction in comparison to the beta glucoside. Even we know that there is a steric component in the alpha glucoside, and since the reaction is reversible, it equilibrate to the corresponding 2:1 mixture, which I mentioned for the glucoside formation, for the hydrolyzed glucose composition. So, let me explain this anomeric effect. What is this anomeric effect? Again, I will draw the chair conformation of the pyron. Here, if I keep a substituent at the axial position, and let me draw another chair conformation where I will keep the substituent at the anomeric carbon at the equatorial position. In the first case, oxygen is having 2 orbitals for the lone pair, axial, these are the axial lone pair. axial lone pair. Now, this anti-bonding orbital of this axial substituent, which is empty, is parallel with the axial lone pair of the pyrrone oxygen. Similarly, I will draw orbitals of the equatorial attached structure. Now, in the equatorial attached structure, anti-bonding empty orbital is not parallel to the lone pair orbitals. Now, what is responsible for the anomeric effect? If the substituent is axial, one of the ring oxygen lone pair is parallel to the anti-bonding orbital of this sigma bond, anti-bonding orbital Cj bond. The molecule then can be stabilized by hyperconjugation, whereas in the equatorial attached structure, the anti-bonding sigma star orbital, which is empty, is not parallel to the lone pair orbitals, and hence the electron cannot be transferred through the hyperconjugation. This phenomena, which strengthens the formation of alpha glucoside, is called like anomeric effect, which is not possible in the equatorial whereas it is possible in the axial. Now, I will talk about the reducing and non-reducing sugars. Reducing and non-reducing sugar. Because glycosides are acetal, they are not in equilibrium with the open chain. They are always in the cyclic form. Without being in equilibrium with a compound that has a carbonyl group, they can be oxidized by the tolerance reagent, and glycoside therefore are non-reducing sugars. Glycosides are non-reducing sugar. Glycosides are non-reducing sugar. Why is it so? As I mentioned that glycosides are acetal, they are not in equilibrium with the open chain aldehyde or ketone in aqueous solution, and without being in equilibrium with a compound that has a carbonyl group, they cannot be oxidized by tolerance reagent. Glycosides therefore are not non-reducing sugars, they cannot be reduced the oxidizing reagent. Hemiacetal, on the other hand, are in equilibrium. Are in equilibrium with the open chain. Equilibrium with the open chain. Equilibrium with the open chain. So, they can reduce the oxidizing agent. So, they can reduce the oxidizing reagent. And therefore is classified as reducing sugar. reducing. Let me explain again. Glycosides are acetal. They are not in equilibrium with the open chain aldehyde R ketone, and that is why these compound, since does not have aldehyde or ketone as a carbonyl group, they cannot be oxidized by tolerance reagent, and hence they are called non-reducing sugar, whereas in the case of hemiacetal, which can easily equilibrate into the open chain aldehyde or ketone form, they can be oxidized by tolerance reagent, and hence they are called the reducing sugar. Now, an acetal is a non-reducing sugar. An acetal is a non-reducing sugar. Again, point to remember is glycosides are non-reducing sugar because they cannot convert into the open chain compound which has carbonyl in its framework. Hence, they are called non-reducing sugar, whereas hemiacetal, which can easily get transformed to the open chain compound which has carbonyl in its framework, either aldehyde or ketonic group, and then they can get oxidized by the tolerance reagent, and that is why they are called reducing sugar. Now, to make you understand this in a better way, I will like to give you an example from our day to day life, that we all are hearing about the diabetes. It is a lifestyle disease, and here it has become very common. In every family we are learning that X is getting diabetes in a very early age, which was not earlier so much. I believe that at some point our lifestyle is getting responsible for this such a early detection of diabetes. For the diabetes test, we generally measure the blood sugar level in our body. So, how does it happen basically? Let us discuss about that. We can understand this in a more elaborated way. So, measuring the blood glucose level in diabetes. Blood glucose levels in diabetes. How do we measure the blood glucose level? The objective here is just to get aware with the with the reducing sugar and the non-reducing sugar. I just now discussed that what is reducing sugar and what is non-reducing sugar. Same concept again I will bring here. So, glucose in the blood stream reacts with glucose in the blood stream reacts with an amine group. Amine group of the hemoglobin. Hemoglobin to form at an amine. It is a simple reaction of carbonyl with the amine group, and that imine subsequently undergoes an irreversible rearrangement. Undergoes an irreversible rearrangement. Irreversible rearrangement to a more stable alpha amino ketone, alpha amino ketone known as hemoglobin A1C. Hemoglobin A1C. Now, I will write it in the equation form, same reaction. So, here I am writing open chain form of glucose this reacts with the amine of hemoglobin in presence of trace acid, as for the here water molecule is coming out. So, trace acid is already there in the biological system. Hemoglobin now, this will go for the rearrangement. And it will get converted to corresponding amine. This amine will get converted to corresponding amine CH2NH hemoglobin, and this internal alpha position hydroxyl will get converted to the carbonyl. This molecule is known as hemoglobin A1C. Thus, measuring the hemoglobin A1C level is a way to determine whether the blood glucose level of diabetic patient is being controlled or not. So, whatever, because it will form from the glucose available in the blood stream by this reaction, that hemoglobin amine will react and it will form the hemoglobin A1C. This one label determines that how much sugar is available there in the blood glucose. And by knowing that, we can easily control our diet, and that way we can know that how much amount is needed. If we are taking excessive intake, then we have to cut down. So, this is our in day to day life, where basically what is happening here, hydroxyl is getting oxidized through this rearrangement to the corresponding carbonyl to form the hemoglobin A1C. This is the reaction taking place while measuring the blood glucose level in a diabetic patient. Now, I will stop here. So, today we discussed about the basically various type of reactions. First, we talked about the formation of glycoside, and then we discussed its mechanism. Then again we discussed about the reducing and non-reducing sugars, and then we talked about the how one can measure the level of glucose in the blood stream by reacting it with the hemoglobin amine, which get by the rearrangement gets converted to the corresponding amino ketone. And we generally while measuring blood glucose level, we measure that level in the diabetic patient's body. Okay. Thank you very much. We will again continue with the next topic.